The three-tier architecture is basically how all SaaS apps are now built. And, like all architectural patterns, it didn't sort of spring into existence when somebody said, what we should really have? We should have a three-tier architecture. What actually happened is people started developing and deploying these apps pretty early, and this emerged as sort of, the apps that work well, what do they all have in common? Is there some structure that they all have in common? And then that gets extracted into an architectural pattern or a rule of thumb or a design guideline. And that's really how it's been for a lot of software engineering, right? We sort of learn after the fact by looking at successful systems and asking what made them successful? What do the successful ones have in common? And can we now distill that as advice saying, in the future, when you build, do this, not that. So where this really comes from is dynamic content generation. And today, when we think of software as a service, that's really what this is, right? Software as a service is there's a program running somewhere that takes input and generates output, but instead of running on the user's local computer, it's running on a server and they use a browser to access it. But that's really not always how it was. When the web began, that's not what it was intended for. Most web pages in the late 90s were plain old static files like HTML and images. And in fact, the goal of the web was to allow scientists to exchange academic papers that had not only text, but graphics and other sort of rich media in them. So in the old days, a lot of web pages were just that. It was a static page. There was nothing that you could really do to it. Forms were sort of a big deal. But the more interesting original web programs were the ones where when you made a request, it was basically running a piece of code that would generate the page, right? And again, today, this is what we think of as SaaS, but someone had to be the first to invent that idea. And the early e-commerce sites were sort of the first indicators that, maybe the web is useful for something other than viewing static content. And because it began from let's view static content, it's not surprising that we think of SaaS applications in terms of these template systems, right? You sort of think of a view as we begin with the HTML that is going to be delivered, but there's a few places in there where code can be run and the results are substituted in. So this sort of template-centric view of the web comes directly out of that. And as we all know, what eventually happened is the part where the code is running, that became the interesting part. Like there's very few interesting static websites around today. Almost every interesting website is one that is actually running a program. So that sort of became the tail that wagged the dog. And as more and more of these apps got built, we started looking at what were the architectural choices that worked well, especially when an app got really popular. And that's where this idea of shared nothing architecture comes from, where you have these three very distinct sort of logical tiers, and each one has a specialized function now, right? And again, when you're running on your own computer, these are sort of smushed down to processes running on a single machine. In the old days, that was also not uncommon, that there would be an actual physical server and it would be running all of these pieces of software. But logically, there really are three different functions here. One of them is just accept web requests from the outside world and send them back. That is a pretty specialized task, and that's what web servers do. The app server is, okay, you got some code you want to run that actually does the work of your app. What is the runtime environment seen by that code? And can we provide support for basic things like plumbing and HTTP so that the app itself doesn't have to worry about it? That's what the app server does. And usually it's the app server in conjunction with some framework like Rails or Django or Flask or Node or pick your favorite. And finally, most interesting programs have to store stuff. And where do we store stuff? By and large, relational databases are they became the go-to very early because even though when web apps were sort of just beginning to come on the scene, by then, relational databases had been around for like 50 years. They were well understood, they were well engineered, and they were designed to give very hard guarantees, the ACID properties, if you've taken a database course, that made them a great fit for the initial web apps. It was better and more reliable storage than most people were able to build themselves. So those are the three logical tiers. And when you deploy, those have to map onto physical hardware somewhere. And when you're developing locally, as we've seen, here's your view of the world. This enclosing gray box is sort of a computer environment. Your browser is running on it. A simple web server, probably WebRick if you've done Rails development. The app server is Rack, and that serves as the host for a framework, in this case, the Rails library. And usually, most of us are using something like SQLite, which provides all of the logical functionality of an SQL database, but it's a single user, single machine, not designed to be used by multiple users. It saves the database in a simple file. It's fine for development. When you go to sort of what I'll call a medium scale deployment, you might see something like this, where now we've got what are called 3 columns, right? Now we've actually broken out the web server into its own separate logical component. We've also given it access to a page cache. We'll talk about all the different ways that you can do caching in Sass, but one of them is cache the entire page until something about that page changes. And then those requests don't even have to touch the framework. Now we've got sort of 3 copies. There's 3 copies of the app server, which in production, you want to use a more hardened one like Puma or Unicorn. The software stack looks basically the same, but now instead of SQLite, we're using something like MySQL, and the single database might have connections from all 3 of the columns. Again, one of the things databases had already been designed and optimized to do is serve simultaneous connections from multiple clients, where each client is an app that wants to use the database. So again, a lot of the engineering had already been done. And as you get to larger and larger deployments, this is more like what Heroku deployment looks like. We still have HTTP servers, but now they're even more specialized. Heroku actually wrote their own HTTP server originally in a language called Erlang, which is somewhat obscure, but it's actually a really good language for doing event-based programming. And that's kind of what an HTTP server does. It waits for something to happen, and it's got to have a lot of requests in flight at the same time, right? So because what it does is simple, a single HTTP server actually can serve a quite large number of web browsers. And so that is a separately provisioned tier from what they call the dynos, which are the processes that run whatever app server, right? We've been using it to run Rails-compatible app servers, but Heroku can support, like a dozen different languages and stacks and frameworks. They run a sort of customized configured version of the Postgres database, which incidentally has its roots here at UC Berkeley. The database has its own query cache, which we'll talk about how to take advantage of. And you might even be serving your static assets, like if your site has a lot of images or JavaScript or big CSS style sheets, those might be served from an entirely different set of web servers and cached in the local Heroku web server so that once it's been fetched once, it doesn't ever need to be fetched again. Right? So the logical tiers are still there, right? There's still the presentation tier, which is just the web server. There's the application tier, which is the logic that runs the actual app. And there's a storage tier. But the way that those map onto specific pieces of software and the way that the software maps onto different hardware configurations, that's what's really evolved, right? And that's why it's a design pattern. The design patterns are, let's capture the things that are the same and identify what things can change. The thing that is the same is the division of responsibility. Presentation, handle a lot of users in flight. Application logic, let the code run somewhere. Storage, make sure you got a place to put stuff and that it will stay there and be secure. So what about this database here? The one thing in common in the 2 right-hand pictures here is there's multiple copies of the app server, but there's sort of only one copy of the database. I've shown the Postgres database with sort of these little shadow copies behind it to talk about the things that you can do to sort of amplify the database capacity a little bit. Sharding and replication are probably the 2 most common that you'll hear. Sharding just means that you partition the data in your database across completely separate fragments or shards, which scales really well. So an example is if you have a website that stores user profile information, the vast majority of the time, any given user is only going to need access to their profile information. It's very rare that you would need to sort of compare the profiles of 2 different users during a session. So it's not a terrible idea to potentially say, we're going to have 3 different databases and just spread the users out over them. The problem is that as soon as you have to do operations that have to cross those databases, things get ugly really fast. So it scales really well, but the situations where you can sort of really exploit it and use it are somewhat limited. More general than that is replication, where you try to replicate data across more than one copy of the database. Again, if you take a database course, there's like a whole module on different ways to do replication and keep the copies in sync with each other. One version of this is called primary and replica, where you can either have one primary that can accept reads and writes, and the other replicas are just copies that you can do reads, but you can't do writes. That works pretty well if your fraction of reads compared to writes is quite high. Or you can actually try to have multiple completely independent copies of the database, and anytime one of them is updated, there is some process by which the others eventually catch up. There is an entire field of distributed systems devoted to how to do that in a synchronized way. But depending on how you set up your database replication, as the end user, you may not have to worry about it too much, except to make sure that your workload, the queries, the kind of work you're asking the database to do is a good match for how you've chosen to set up your replication strategy. And enterprise platforms like Heroku support a variety of database replications. It's basically how much are you willing to pay for how much redundancy you need. The sort of key takeaway here is, in terms of the number of web servers and the number of app servers, if you need more capacity, just add more columns. That's easy, right? Because they're stateless. The only state that matters in a web session is something that is stored persistently somewhere. That could be in a cookie, but that's fine because the cookie gets passed back and forth. Or it could be in a database. But the database itself is not trivial to scale. You can't just put up multiple copies of it and expect it to work. You have to talk about, are you doing something like partitioning and sharding? Are you trying to keep the multiple copies in sync? And if so, whose responsibility is it to do that? Right. So as you'll see, a lot of the techniques we talk about for maximizing your bang for the buck when you deploy is be nice to the database. So that will be the subject of the next couple of sections.